Good morning and welcome to another topic related to the operation. Okay, so today the topic that we'll go for related to the LLM model summary. Okay, you all must be knowing what is Hugging Faces, right? Consider this is the GitHub for the all the large language models. Okay, where these different parameters goes on that, right? When they create these LLMs, you see multiple things on that. Let's say if we go for this Hugging Faces and one of the model, right? Okay, let's go to this model. You see a lot of informations, right? So one of the information that we'll go for now is trying to understand is this particular thing, right? The model summary. Okay, so these are more internals related to the operation team or anyone to do, because it's not just running the model, right? Most of the video what we see is related to the running of the LLMs, right? You ask questions, GPUs and everything. But consider this, when you spin up a LLM, when someone queries to LLM, right? It goes through the AI load balancer, how exactly it goes through rest of the routing, how exactly you do the multi-data center, how exactly you get into the each GPU mapping, everything that it get into the operation sides of this one, right? Before getting into those kind of things, we will go through a little bit more about trying to understand these parameters. Okay, this not to confuse with the parameters of LLM parameters. Let's give them the naming convention of called as features, right? That would be easier. Okay, so this is one of the sample model that I took for going through the model features. Okay, let's go through. This is what you actually see: the architecture, total parameter, activated parameter, number of layers, number of difference layer, attention layer compositions, attention hidden dimension, number of attention head, latency MOE model. Okay, MOE hidden dimension per experts, number of experts, selected expert per token, number of shared experts, vocabulary size, context length, attention mechanism, activate function, vision encoder, parameter of visions encoder, quantization and modality. Okay, so in this video we'll go through a little bit quick overlook, but we'll do a deep dive of each of these on the further sequence. These are the further deep dive you can see. Okay, we'll go through that one. It's not easy accessing each these models internal parameter on real world, but let's understand a little bit. Whatever based on need, we'll go through a little bit practical on that. Okay, architecture. So what is architecture, right? So in the architecture features, we specify different type of model specification. In this, if you see, it's a mixture of expert, right? So you can get different variant of this particular type. So for example, difference model or other things. But let's try to understand what is this experts, right? So consider this. So when you do a query, when you ask to LLM, right? So we have different experts on LLM that roles are differently. In the analogy, if you see, so based on this particular thing, when a LLM request comes, the router inputs the specialized subnetwork, right? The routes where the requests are there, it routes to a proper experts, right? The analogy what you can think of is when you go to a doctor or hospital, right? For a specific disease, you might not need to meet all the doctors within that. Something very specific to that particular diseases, whatever the recommended expert, you will going to meet it. Consider that one is the architecture of this one, right? So one of the architecture of this one is MOE. We can go anyway, more details of this one is, but for now let's understand a little bit. Over here is this, right? Instead of running one monolithic neural networks. For every token, the network routes input to a small number of a small subset to specialized subnetwork or experts. Okay, this is one analogy, right? Okay, we'll go through that one. So what is next? The total parameter, right? So this is what the total parameters, what it looks like. It means when these large LLMs models are there, it works on these, how many total parameters it need to compute before that. And how exactly, so far each parameters takes around 2 bytes, which is 16 bits. Okay, and researchers are working to reduce the size, so everyone need to load that particular LLM models onto their memory, right? But think in this, when the memory size is too much, how exactly they will distribute that one? We'll go through those kind of things on a distribution, on AIOps related or LLMops related, different topics, what you can see over here. Okay, coming back to the original topic. Okay, so as by default it takes somewhere around 2 bytes, not somewhere around 2 bytes. The models are right. So if it is a 2 GB of I mean 2 billions of this one model, then you consider how much it will take memory, right? 1 billion, so it's a twice of that one, so it's become a 4 billion. So you need a 4 GB VRAM. Okay, either you can go for VRAM or either you can go for unified memory, but more or less you want those memory to be, those big models need to be on the memory. Consider this, when these particular per parameter going from 2 bytes reduced to, which is 16 bits, to reduce to 4 KB, the size what you see, the 4 GB models takes around 8 GB of memory. It will reduce to what, by 4, so somewhere around within 2 GB you get all these models to be loaded within that, right? So those kind of things are working on. Okay, so what is that? Is the total capacity and stored knowledge base across all the subnetwork. So that's called as total parameter. Analogy, a university library holding 2.8 million total reference book that they have to reference back. Okay, what is activated parameter? Okay, what it says. So over here the activated parameter is 104 billion, right? So concept, the actual subset of parameters powered on an calculator for a single token. You don't have to do all the books, right? So pulling only 104 books of the library itself to answer a single research question. So this is called activated parameter. So in further we can see how exactly you configure the LLM YAML files, how much need to be loaded, and based on that how much quicker it would be, how much memory, how much GPU time it will take. Based on that it goes. Number of layers, right? Consider the sequential processing step that refined information from inputs to output. Okay, analogy, a 93 stage assembly line for customer vehicles. Okay, so before it production it goes through all these different assemblies. So that is what called as number of layers. Okay, you can consider somewhat around the Docker layers also. Okay, next, the defense layer. It is the layer where all the parameters are get activated. It's if you do the example on the car, right? This is the point where every inspection get done. Okay, so in this model we get one defense layer. Okay, which where it checks all the input tokens and then it works on that one. Okay, what is attention layer? Okay, combine kernelized attention, fast context. Okay, so let's say this is more or less the example of Apple that you are seeing, right? If we say Apple, what is the meaning of that one? So if we say I like to eat apple or tasty apple, it means it's food, right? So if someone says apple stock, it's about the Apple company. Okay, similar like that, based on the related context, you get some values, right? So that is the attention one. So another parameter called as attention hidden dimension, the width slash capacity of the vector representing concept in attention layer. So it's all about the vector database. The vector database is like when you see image, how exactly they associate the image within the multidimensional parameter, right? So this is where you get a layer where you do the association within the vectors of a given graph. More detail of each topic we'll go through later, but let's have some ideas, like when you open up a Hugging Face and when you open up a model, within that what that you see within the number of attention head. Okay, what it says, parallel stream looking for advanced contextual relationship simultaneously. Okay, so 96 separate inspector examining a contract at the same time for a different detail. Okay, so everyone have specific detail that need to observe for. Okay, latency. Okay, latent MOE dimension. What is that? The summary sheet given to a dispatcher to route a service call. So let's go through analogy of this one. Okay, this is MOE hidden dimension per expert. It's like the workstation size and toolkit available to each specialized doctor. Okay, think about that one. The internal processing capacity of each individual expert model. So we see we have expert model, right? The request goes to a specific expert. So over there, what are the different parameters each expert get it? That's what number of experts is like in that total model. How many number of experts are there? Not every expert. It's like the hospital where you can see 896 doctor, but for your work you might go for a 16 different doctor, right? So that's the number of experts. Okay, selected experts per token. Consider this one. How many experts are chosen to process each individual words a token, right? Over here it says 16 different experts are there for that particular one. Okay, number of shared experts, it's like 2 master supervisor who remain on the site continuously regardless of who is working. Okay, experts permanently active for each every token handled, universal logic. The next one is vocabulary size, the lookup directory of unique character words and code snippet, having a directory that recognizes entire complex technical jargon terms as a single word. Okay, it's 160K for this particular model. Context length, it means there is always test are there that even if you have a bigger context length, it doesn't mean you will get everything quickly. Okay, the active memory window the model can process in a single request. It's like a massive whiteboard spinning an entire room that holds several full book at once. Think of that. The higher context length, the better it is, but 1 million is more than enough, I would think. What is attention mechanism? It's like optimize mathematical algorithm to prevent VRAM running out during the long context. For example, when we see about Apple, right, related to that, so it not everything need to be goes through all this context, right? Not parallel everything. So think about that. A small filing system that compress achieved document, archive documents without losing key facts. Okay. Activation functions, it's like what is that? The mathematical gate deciding neuron firing intensity. Okay, a smart dimmer switch that fine tune electrical signals flow based on the context. First, vision encoder. Okay, a vision transformer that turns visual pixel into vector concept for that particular text. Think about an image when you are pushing something, right? When you enter a image as input, this is what it actually work on. Parameter of vision encoder. How many parameters are working? Over here is 401 parameters are working. 401 million parameters are working. Okay, quantization. It's ultra compressed numerical precision trained natively to save hardware memory. Per fabrication modular built block for standard size of construction using minimal waste. Okay, and modality. Okay, the text or image. Okay, the input and output format the model natively understand. For example, how what all the input format what you give, you write on the text, you give images based on that. There are multiple hacking systems also there. For example, a base 64 encoding things are there. We'll go through those on a other videos. Hopefully you got some context out of it. There are a little bit more examples on each of these further related to that one, and the detail have more expertise things. You can visit to the site called sretoolkit.com over there and you can get it. I'll anyway share this link of this particular summary along with the video. Hopefully you got some idea. It's new things are going on, so it's a learning for everyone. Okay, thank you.